Hi, everybody. Thanks for joining this session today. We're going to talk about pyroclastic density currents. And thanks for those who put already some results into the Padlet from last week's session about lava flows. I was just looking at them and some good results from Lava 2D, for example. So that is great. Keep doing it. And then I don't know, Sophia, if you can open a new folder for pyroclastic density currents. We're gonna do the same thing today. We're gonna use mostly the Titan 2D model, and I'm gonna also show you another model that is called IMAX, that is also running on Victor. So what I would like to do to make sure that you guys have some results before the end of the session is if you can directly install Titan 2D. So I'm going to share my screen. So if you can go into your Victor Hub and open a terminal and then type Victor setup and then choose the model number 21, which is Titan 2D, and then press enter and then wait for the files to be installed. So you should get a new folder called Titan 2D here on your directory, and if you open it, you should have these 4 different files here, including a notebook. So if you can open the Titan 2D notebook, and then if you can go through the cells, I'm going to go back to that notebook later on, but if you can go through the cells right now one by one until you reach the cell number 6, I think, which is called material model. And then once you reach that cell here, I want you to change that number here that is called the battle friction angle. So I'm going to leave it to 25, but I want you to choose a number between 8 and 25. Okay, so any number between 8 degrees and 25 degrees. So just change it here in that cell. Once that's done, you can keep going until you reach the cell where we're going to actually run the model here, cell number 12. And then for here, you're going to have to wait a little bit because it's actually going to run the model. So that's where you can stop once you reach cell number 12, and then you can check the progress of your simulation here. And then we're going to go back to that later on. Okay. And I'm going to explain you exactly what the model is and what are all the cells doing and what are the input parameters. All right, so let me share my screen and tell you a little bit more about pyroclastic density currents. While we're running the simulation. So as you know, pyroclastic density currents are one of the most dangerous volcanic hazards. They can occur at any volcano that generate explosions or that have a dome that can gravitationally collapse, or that have even just hot perch material that are accumulating on the steep slope and are unstable. So the range of pyroclastic density currents is very diverse. It goes from gas-rich end members where gas is mostly dominating the dynamics and the mobility of the current, to dense members where mostly the solid particles are the main driven mechanism. So due to that whole range and spectrum of currents, from gas-rich to solid-rich, we're gonna have to use different modeling approach, and we're gonna have to make some simplification due to the billions of particles that are included in these currents, and due to the multi-phase nature of these currents, there will be some simplification to do in order to make some simulations that don't take months to run. Um, so one of these simplification is a source generation mechanism. So as you know, progressive density currents can be generated from different source mechanisms. So for example, we can have a dome, a lava dome that can collapse. That dome can also explode. And based on whether it's going to just gravitationally collapse or explode, we can get progressive density currents that are going to be mostly directed towards one valley, one drainage basin, or be generated all around the vent at 360 degrees. Um, it can also explode on one side and generate what we call a directed blast. That's what happened at Mont St. Helens, for example, in 1980. And in that case, all the momentum are going to be directed towards a particular direction down the flanks of the volcano. So it can be the collapse of an eruptive plume or eruptive column. So generally that happens when we have sustained Plinian eruption or subplinian eruption, and then some changes occur at the vent due to the change in the mass flux of the material, so the column becomes unstable. So we don't have enough air entrainment, so the density of the column itself increase, and we have the column that can collapse on itself to generate column collapse, Pyroclastic density currents. And then we can have also the last type here, which is the most, not really the most common, but that have been observed at some volcanoes where instead of having a subplinian or plinian column, we just have some fontaining. So mostly a weak plume that is going to generate mostly some Hawaiian fontaining at the vent that can then lead to some collapse of a very high mass flux of hot material that can then transform into Pyroclastic density currents. So based on that, once the PDC starts, then it's going to be transported downslope, and from there, there's several models that can describe how the mixture of particles and gases can couple together to actually form the PDC that can then move downslope. So the models have been changed over the years, and I wanted to show you only one of the last models that have been put together by several people during the last, I would say, 10 years, 10, 15 years, where we tend to go away from that, I would say, B dispersed model where we have, the dilute and then the dense type. Now we recognize that there is a whole spectrum of type of PDC that correspond to a spectrum of particle volumetric concentration. And so instead of having only the dense and dilute model, we tend to now agree that there is also an intermediate model where the coupling between the gas and the particles are going to change from a one-way coupling to a two-way coupling, and then a four-way coupling when we increase the particle volumetric concentration. And in this intermediate regime, you can see that that's where we're going to get some clusters of particles. So we're going to move mostly from dilute suspension to some collisional forces that are going to occur between the particles before they become too abundant to really collide, and the frictional forces are going to dominate. So you can see that the range of particle concentration from this intermediate regime here goes all the way from 10 to the minus 4 to 10 to the minus 1. And so this wide range of particle concentration allows this intermediate regime to be the main regime that we're gonna see in most of PDCs that contain some moderate amount of gas and particles. Um, so from there, then we can try to build some conceptual structural models for each of these type of PDC. So here I'm showing you only the two end members, which are the dense one and the dilute one. But you can also get the similar conceptual structural models for the intermediate regime as well, where the clusters are gonna dominate here. So you can see how the coupling between the particles and the gas is going to change from the top of the current all the way to the base when we have an increase of particles towards the base of the PDC. It's going to allow some four-way coupling to develop there. You can see here the difference between the vertical profile of solid concentration in black and then the velocity profile, how that changed from the dense regime to the dilute regime. Keeping in mind that, of course, a PDC can actually transfer from a dense to a dilute or a dilute to a dense based on particle settling, sedimentation, and air entrainment during the transport. So this complex multi-phase mixture is not really easy to model, right? And so depending on how much complexity you wanna put into your model, uh, we're gonna have to do some simplification, like I was saying at the beginning. So here is a table showing you a list of models that can be used to simulate pyroclastic density currents, and you can see that for the same same as for the types of PDC, we have a wide range of model and modeling approach. So we start with here statistical models like the energy cone model, for example, or the energy line model, or some models are going to look at the area covered by the PDC and the volume of the PDC and do some statistics based on that to try to predict how far a particular flow can go inside a channel. So this is a PFD model, for example, I'm going to show you next. And then we have also molasses that we used last week for the lava flows. It's also a model that we can use for PDC. There's a PDC version of that that include a modification of the volume to include gases in there. And then we have the pyroflow model that is more like a kinematic model. And then we move to two-dimensional model here, where we're going to include some conservation equation of mass and momentum, keeping the mixture incompressible for most of them. But you can see you can have them in 1D or 2D, and most of these models are called depth average model because we assume that there's no variation in the vertical along the height of the PDC from the base to the top. That's a big assumption, right? Because I was showing you before that there's actually some variation, right, here in terms of solid concentration and also velocity. So we assume that we have a straight line here that is vertical line between the base to the top. So this is a pretty big assumption, but that's going to allow the calculation to be much faster than if we also change some of the flow properties in the z-axis, and that's what multi-phase model are going to do generally. So, for example, I'm going to show you two examples: MFix and PDAC, where this time we have three-dimensional domain where we treat the mixture as a transient and compressible. So then volume and mass can actually change during transport. And generally, we also include an equation for the energy, which takes takes into account the temperature inside the current. So these are more complex models that generally cannot be run easily on an online platform or because they require a lot of computational resources to run. So talking about statistical modeling, like I was saying, we have the PSD model, where we're going to look at some statistics of previous past pyroclastic density currents. So some of the metrics we can use are the H over L ratio, right? So the horizontal distance divided by the vertical height divided by the horizontal distance, and we can plot that against volume. And you can see, for example, here that different types of PDC have different H over L ratio, but what we can see is that they all show a decreasing H over L ratio with increasing volume, which means that your volume is basically already a very big parameter, important parameter to control the mobility of your PDC. Something else you can do is look at the area against the volume. So you look at the footprint of your deposits and you plot that as planimetric area or cross-sectional area if it's a channelized flow, and you plot that against the volume on a log-log scale, and then you can end up with some coefficient A and B here that can be used to simulate a PDC inside a channel and try to get a runout distance, so try to see how far the PDC can go. So it was initially developed for Lahar using the Lahar seed model. We're going to see that next week, I think. But there was also a version for PDC made by Sarah Ogburn using the FlowDat database here. So that FlowDat database, you can click on the link and only to show you that website here. So this is from USGS, and it's a database that regroup a lot of different mass flows, especially Lahar and pyroclastic density currents. And what is this table is showing you is some metrics of different flows and different flow types. So you can use this database, for example, to try to look at what is the mean value for volumes of, let's say, block ganache flows or volumes of small volume column collapse PDC, for example. And so this database is updated often by Sarah. And you can see here, you can download the last metadata with the last database, the SQL file. And you can basically use that database to constrain some of the parameters that you may need to simulate a particular PDC at the volcano that you're interested in. So I really encourage you to look at that mass flow database. Okay, so these models, what we call statistical models, they don't use any physics, right? They just use statistics from past PDC, and we build what we call a statistical model based on some best fit regression of the data to actually simulate PDC. So they're generally good for only one channel or one particular drainage basin, for example, around the volcano. So moving on into a little bit more complex model, then we have the depth average model. So that's the one you're gonna see on Victor. So we have all three of them here on Victor: Titan 2D, VoltFlow, and IMX. VoltFlow can only be run on MATLAB, so you need to request access for that. That's a limitation of big limitation of VoltFlow right now. Rather than the two others can be run via Jupyter notebooks or directly on your desktop. So all of these three models are using what we call conservation equations for mass and momentum. So these are the equations here at the bottom. So the first one is the equation for mass conservation here, where U and V are the velocity, horizontal velocity in X and Y coordinates. H is the flow height. T is the time. So you see that this equation is just looking at the rate of change of the uh, the mass as a height, as a flow depth, basically, as a function of time, and then the velocity vectors in the x and y direction. And then the two other equations are what we call the momentum equations. So one is in x and the other one is in y direction. Um, and basically, what these equations are solving are the driving forces on the left hand side here. So all these are driving forces, so flow acceleration, basically, um, and balance on the right hand side by all the stress that you apply to the flow. So the first term here on the right hand side is the stress due to the weight of the flow, h, alpha being here the slope angle. And then the second term here is what we call the earth pressure coefficient. So this is valid when you're using a frictional rheology, using some friction angles. I'm going to show you that after. So we use this coefficient here, K active passive, which can be positive or negative if the flow is converging or diverging from one cell to the other. And it's basically using it's related to the internal friction angle and the basal friction angle of the flow. And then here you have the retarding stress, this last term here, and especially this tau value is going to be your rheology. So what kind of rheology you want to apply to the flow to actually slow down this momentum here on the left hand side. So similar to lava flows, what Enad was mentioning last week, we have different rheologies that can be applied to different types of currents for PDCs. So one of the most common is called the Coulomb rheology that use only either one angle, which is only the basal friction angle, or two angles, which is going to be the internal friction angle and the basal friction angle. I'm going to go back to these after. So that's basically what you just change in the Jupyter notebook at the very beginning of this session. That's this basal friction angle here, phi bed. We can use a viscous force, but it's not really used in PDC. The problem with viscous force is that you're going to allow the flow to keep going on very slow, low slope angle. So it's not very valid for PDC. So the other thing we can use is a Volmy rheology, which, in addition to the Coulomb term, which is a mu value, is going to use a square velocity drag coefficient that's going to be related to the turbulences inside the flow. So this is this epsilon value here that you have on the right side. You can also try to use a plastic rheology that assumes that the shear stress is constant relative to the normal stress. So for that, you're going to use only a single value of the retarding stress. You can add to this plastic rheology what we call a square velocity coefficient, epsilon, same as what we were using in the Volmy term here. You can add that to your constant retarding stress and have a new rheology here. And then finally, you can use a Bingham rheology like we were using for lava flows, using a plastic plus a viscous term. So you see that, there's a whole variety of rheology. These are just examples here, but there's also the mu-I rheology, for example, that varies this Coulomb term mu based on the inertial number. You also have the Pouliquin-Forter that use also a varying friction angle based on the thickness of your flow. So there's a lot of variety. So it's not easy to know which rheology to choose. And generally, there's not only a single solution. You can test them and see which one is actually working the best. And that's what we're gonna look at today, using different values of the bed friction angles. And then with IMEX, we're gonna use the Volmi rheology just to show you the differences between them. So going back to the three models that we have available on Victor. So here are the list of some of the differences of these three models based on the platform that it's using, the numerical framework. Titan 2D is using this adaptive mesh refinement that is different from just the normal finite volume solver from Voltflow, or the one from IMEX that is a little bit more complex. It was using the Hunja Kuta method. The rheological law, like I was saying, most of these models allow you to choose between different rheologies now. IMEX having more than 11 different ones now. I think there's even a 12 one now. And then the type of processing, most of them are using parallel processing, except for Workflow that is using only a single processing on MATLAB. And then source code available for Titan 2D and IMEX that is not for Workflow. Something that is also important is the format of your DEM, that all these three different models are all running over digital elevation data that has to be in a particular format. So some of them are more flexible, like IMEX, that can use any GDAL format, or others are more restrictive, like Voltflow, that is only using Golden Software Suffer format. And then Titan is using either a GraphGIS format or a GDAL format. Right, so before going through the notebook for Titan 2D, let me just show you what the Coulomb rheology is. So we have two friction angles that we need to input. One is the internal friction angle, which is the steepest angle that the upper surface of a conical pile of dry sand can make with respect to the horizontal plane it's resting on. So it's more like an intrinsic parameter for your material itself. So this is the code Titan 2D is not really sensitive to that parameter, a little bit, but generally values for this internal friction angle can vary between 25 to 35 degrees, based if you consider having mostly solid particles or a lot of fine particles at the beginning of your current. But this is not the most important parameter. The most important parameter is the bed friction angle, which is the angle that a plane needs to be inclined so that your material, your PDC is going to start sliding downslope at a constant speed. And so, of course, you can see that using small value is going to allow that PDC to go much further down than if you use large value. So that's what we're gonna test how that bed friction angle is actually um, related to the mobility of the current. So let's go back to the notebook. So maybe most of you have completed the simulation. So for that, you can move to the other cells then. You can plot the output. So for example, the first one is actually showing you the first time step in the simulation over the DEM, it's just a way to check if your initial pile of material that you started with is located at the correct location that you want it to. And then the second one is going to actually compile all the different output files into a single one to actually give you the entire footprint of your simulation by using that pile height record file here. that is actually recording um, the maximum flow depth at any time step during the simulation. All right, so this is the output that I have. I didn't change the friction angle, so I keep it at 25 degrees, and so I can see that my flow was sloping down the south flank of Merapi volcano here, and stop when the valley get pretty narrow here. Uh, didn't go over that ridge here. Um, so I would like you to save this output and copy it into the Padlet, so then we can check for those who change the battle friction angle to lower value than 25 to see what is the footprint that you guys got. So please do that by adding your results into the PDC folder here on the Padlet. So while you're doing that, let me just go back to the beginning and describe a little bit what this notebook is doing. So first, you import all the libraries that you need in order to run the Titan 2D model. Then there is a user guide that you can download here. So please look at this user guide. It's very useful to learn more about the model and then the different input parameters. So I'm actually going to go directly to one that I want to show you. Okay, yeah, this one. I added as a link before, but it's going to work. All right, so make sure you read that user guide and then the references that are also included in the user guide. Okay, the first thing you need to do is to choose the format of your digital elevation model. So here you can see that we use a GDAL format, so that's going to allow you to import some GeoTIFF digital elevation model. So that's one of the one we're using here is a DEM from a Merapi volcano at 15-meter resolution. So one thing I would like you to do during the week is to actually import your own DEM for your own volcano and actually run Titan 2D on that volcano. So for that, you're gonna have to change that line here by putting the name of your DEM. And then you're going to see that you're going to have to change also the location of the source because the coordinates for the source location are going to be different, right? These other parameters here, the scaling parameters, are actually for trying to scale your simulation. So it's to avoid any error when we round off, when the code is going to round off the values for the flow properties. So, for example, you have a lane scale here that's in meters, and that's basically how long you expect your flow to be, like the run out of your flow. It doesn't have to be an exact value. It's just an order of magnitude, right? If you think it's a couple of thousands of meters, or if it's more than tens of thousands of meters, then you can input it here. That's going to help the simulation to be a little bit more accurate, but not crucial. Here, you set the maximum iteration of the simulation. So you can do that by a maximum number of time steps here, or by a maximum time. I really strongly suggest that you use a time instead of the time step, because the time step, you have no idea how many time steps you're going to need in order for the flow velocity to go down to a background value between like 0 and 5 meters per second, let's say. It's never going to reach 0 because that's how the depth average equations are set up. So your velocity cannot be 0, but it can be very close to 0. And you want that. You want that flow to actually almost stop at the end of the simulation. So I would suggest to put a very large number of iteration, like here 100,000, and really take put a time that is in a second for your simulation to end. So here we are simulating a very small PDC that is only, I think, million or a little bit less than 1 million cubic meter. So that's why we put a time of 80 seconds, which is enough to actually get the flow velocity to reach background value. So you can check that if you go directly to your running cell here, and then you look at the last time step here, you can actually get the velocity. So you see average velocity here is 1 meter per second. So that's good. That means that my flow actually stopped when the simulation stopped at the end after 1 minute and 20 seconds. So you can check that. So if you see that your velocity here is still very high, like 10 meters per second, for example, you may want to go back to that cell and then increase that maximum time so that you allow the velocity to reach background values. Then you can set up the format of your outputs, and so you can do that here by selecting one of the formats that Titan allow you to select. The most common is this XDMF because it's actually a format for plotting all your output into a software called ParaView. And ParaView is really powerful because it allows a lot of different files, types of files, and you can do a lot of things with ParaView. And we actually have ParaView on the desktop, so you can actually even open it on the desktop for plotting your results if you don't want to use the plotting tools that are at the end of this notebook. All right, and then the two last parameters here are the interval for the model output. So you can do that by iteration, but again, you don't really know how many time steps correspond to an actual time in the simulation. So I would rather use that time parameter here. So here you can see that every 10 seconds we were saving a file. So you should have 8 files, right? One every 10 seconds until you reach 80 seconds. So you can change that number. For example, if you want to do if you want to create some movies, some animations from your simulation, you can put that pretty low to like 1 second, every 1 second, for example. Be careful. You're going to get a lot of files that are saved into that visout folder here. So you want to make sure that you got enough storage space. If you end up having 100 files or more in there, each of these files are pretty small. It's like 100 K here or 1 megabyte, but then you can end up quickly having a lot of files that's going to grow there. So make sure you don't put a too small number here. Next cell is about the numerical parameters. So I was mentioning earlier that Titan is using a numerical solver that is going to do some adaptive mesh refinement. So you want to keep that because that's how Titan is working the best. I'm going to show you exactly how we do that, how the code is doing that. So in addition, you're going to select that number of elements across the smallest pile axis or the smallest flux source at the beginning of the simulation. And that's related to, so if I open the user guide, that's related to this graph here on page 27, where we're showing you how we're going to divide the cell of our grid into smaller and smaller cells based on how much is our smallest axis in our ellipsoid here for our pile or for material pile. And so the number that you put in here correspond to how much you're going to divide that smallest axis. So basically, you can see you take the length of that axis and then you divide it by 16. That's what the code is going to do at the beginning to allow the simulation to be a little bit more accurate. Okay. So you can see here the minimum cell size allowed is reached when the cell containing this pile center is no larger than the smallest pile diameter divided by the number of cells across the smallest diameter of your pile. And then there's some secondary refinement to actually maintain one level of irregularity between the cells. That is made automatically by Titan, whether you use a first order here or a second order solver method. The first order is going to average the value across an entire cell. So all the flow properties like the flow height and the velocity are going to be averaged over an entire cell. The second method, if you put second instead of first, is going to allow some variation of computation along the same cell, the same pixel. So it's a little bit more accurate, but it takes more time. So you may have the simulation that's going to take more time. I would say that as long as your DEM is pretty fine resolution, is good enough, then you can keep the first order. It's just if you're using a very coarse DEM, like SRTM, for example, you may want to change that to a second order. All right, and then after you have the material pile, so that's where you, the material cell, that's where you put your rheology, right? So you remember you can choose between different rheology. So you have the Coulomb rheology, that's the one we're using here. You can have this two-phase Pitman rheology, which is for if you want to simulate lahars. We're going to talk about that next week. But that's one way that you can simulate lahars with this code. The Volmisarm rheology is this Coulomb rheology together with this turbulent coefficient here. So that's basically here how you enter it as a mu for the Coulomb term, and then a Z for the turbulent term. And then you have also the Pulliker-Forter, if you want to vary the friction angle based on the thickness of the flow. So that's how you're going to use these different values of phi here, which are basal friction in degrees. And then you have also a parameter beta, and then an L material parameter. You can learn more about that in the user guide and also in some papers that have been written for using that rheology in Titan. Next is the pile material. So you can simulate the generation of your PDC as a pile of material that's going to be on top of your DEM, right? So generally we use either a cylinder or a paraboloid. So if you want an ellipsoid with different minimum and minor and major axes here, you're going to put them here. That's where you put the center of your pile. So that's your coordinates. So for those who are going to try to use their own DEM, you're going to have to change these coordinates here. These are in UTM, north and east. So make sure that you change that for your own volcano. You can define an orientation for the pile. You can look at that in the user guide. You can also change the initial velocity and then the initial direction of the pile velocity. If you want to simulate a directed blast, that's where you're gonna actually put an initial velocity here with a direction. And then here is an option to put a volume fraction of solid if you're using the lahar version, lahar rheology. Instead of a pile of material, what you can do also with Titan is to add a flux. So instead of starting already with an initial volume, you can say, okay, I want my volume to be added through time during the simulation. So that's how you're going to do that here. You're going to select an influx value with a start time and an end time, center of your flux, and then the radius, major and minor radius of your flux. So you can do that as well, either in addition of your pile or instead of your pile material. Discharge plane, you can actually verify if your flow is actually crossing a particular drainage basin, for example. So you define the boundary of a box where the flow is going to pass through, and it's going to give you some values of the velocity and flow height across that box. All right, I think that's all. So then that's all for Titan 2D. So let's have a look again at your at the pilot. Cool, we got some results. Perfect. All right, so we can see that some of you were using lower values of friction angle, and then You can see how that changed the footprint, right? You can see that the flow went much further down the slope of the volcano, and we're able to overtop that ridge. So that's what I wanted to for you to do. So uh, you know, let me jump directly here. Yeah. So these are some other tests that I did for my PhD, and on the same volcano, same drainage valley, and showing you how varying that friction angle can actually have some dramatic impact on the footprint of the flow. So you can see here, if we decrease to 16 degrees, I think I was using a bigger volume here anyway, but you see how that the flow is actually jumping, spill over that 200-meter ridge that is here on the east side. When you use 20, it's not doing that. And then one way that I've found to actually have a better match with my observed footprint that is in red here is to actually vary the friction angle from the top here to the distal part of the flow, and I was decreasing it from 24 to 10 degrees in that case. So you can do that in Titan by using what we call a material map. So if you open the user guide, you're going to see that we can actually use you can actually use a material map with Titan 2D that's going to allow you to to define your basal friction angle based on yeah, here material model and map. You can actually to be able to select different friction angle values based on um, either the roughness of the terrain, or the slope angle, or whatever you want, and that's actually allowing you to get a little bit more realistic simulations. Um, so eventually, that comes to the fact that when your flow is actually sloping down the volcano, there's going to be some entrainment of air, right? There's going to be some settling of particles. So it's going to evolve, right, from different regimes, like I was mentioning before, from the dense to the dilute to the intermediate regime. So you want to capture that in that rheology. So that's why instead of using a single constant value for the basal friction angle, uh, I think now the new models are actually changing the basal friction angle based on some parameters, either from the topography itself or from the flow properties that are actually changing through time and spatially. Another thing I wanted to mention is that you need to be careful of the DEM resolution. This is some simulations done with three different DEMs. One is the local DEM that you are all using now, using 15-meter resolution. But if you do the same simulation with the same parameter on a Aster DEM and or an Aster TM DEM, you're going to get completely different results. So make sure that the rule of thumb is to get the most precise DEM as you can. Try to get the resolution to be, as good as you can, and the vertical accuracy also is very important because you want the topography to be correctly reproduced on your digital elevation model. So just remember that these models are really sensitive to the topography that you're using, and so the quality of the DEM is very important. Last category of model before I show you quickly IMAX, the IMAX um, notebook is called multi-phase flow model. So two examples are PDAC and MFIX. So you can see here that the equations become a little bit more complex because this time we got different solid particles of different sizes, different gas species as well. We also include the enthalpy for the temperature of the gas and the solid particles. So this becomes, yeah, very complex, and so very difficult to run these models on a normal computer or on some servers. You need to use some clusters or some supercomputers to run these models. What you get in the end is some footprint of, for example, total volume particle fractions here, or temperature, gas temperature, for example, around the vent. So you can do much more things with these models related to the dynamics, the internal dynamics of the currents. And then another example here is MFIX, where you can also get a volume fraction of solid, the Richardson number to look at air entrainment inside your flow, and then also here the gas temperature. So all this is in 3 dimension, right? So you can do some cross profile or along profile of each of these parameters. So you can go pretty far with these models, but they are computationally pretty intensive and difficult to run on our platform. All right, so finally, I wanted to move into IMAX. So if you go back to the terminal, you can install IMAX the same way you were installing Titan 2D. So this time you're going to select model number 9 here, which is IMAX S-Flow 2D version 2. It's different than the IMAX Lava, okay? IMAX Lava is for lava flows. This one, S-Flow 2D, is for pyroclastic density currents, pyroclastic avalanches, lahars as well. So make sure you select the correct one. So once you install it, you're going to get a new folder called IMAX 2D here that's got a DEM folder and then an executable. If you double click on the DEM folder, you're going to have some files here, including a Python notebook here that's going to allow you to run IMAX. So IMAX is running a little bit more slowly than Titan because it's got much more parameters. So it's still a depth average model, but it allows you to input a solid and a gas phase separately. That's going to end up being a mixture in the end, but then you can select some parameters for the particles themselves. So the size of the particles, the grain size distribution. You can also have parameters for the temperature of the gas. So there's also an energy equation for the temperature. So temperature of the gas is also taken into account there. So it's a little bit more complex. There's more cells. You can just go through the example we have here, which is a small pyroclastic density currents at Colima volcano. It's going to take a little bit more time to run because you're going to have it's going to create some output files every 5 seconds, and it's going to be a little bit long in the end. But once you get it completed, you're going to actually get an output that looks like this, okay? Where in that case, we are looking at the flow depth and then the temperature here on the right. So it's showing you clearly the footprint of the flow at Colima volcano. If you want to know more about IMAX, you can look at the best is to go to their GitHub page, which is this one. I can put the link on the chat here, and I can also answer the question. So the GitHub page is the best to actually get some information about the recent development of the code. They still don't have really a user guide, so what you can do is also look at this paper. That is a description of the model from Mattia. Putting the link here as well. And so reading the paper and looking at the examples here in the GitHub page, you can see that there's a lot of examples already available for you to look. Some of them already have include the parameters, the input parameters that they use to actually get some of these examples. For example, here they use the rheological model 11, which is the mu I rheology And then these are the parameters that they use for this dam break simulation. So you can you can look at that to get more information about how to set up the input parameters if you want to run it for your own study and get a different output here for your volcano. Okay, let me stop sharing and then go to the questions here in the chat. All right. Let's see. Okay. Yeah, I'm gonna make the slide available on the shell folder. I didn't have time to do that, but I will do that as well. Yeah, so I mean, I don't know. I managed to run the simulation in 5 minutes this morning. Yesterday it took me like 25 minutes, so don't worry if it's a little bit slow. Yeah, like Sam was saying, sometimes it depends on the machine you choose, but even like you know using the same machine, I got different runtime from yesterday and this morning, so it can be pretty slow. As long as you don't have any error message coming up, then it's good. If you see that the simulation, I got that yesterday. My IMAX simulation was actually stalling and not responding anymore. So for that, you're gonna have to restart the kernel and restart the simulation from the beginning, and that can happen as well. Um, all right, I see Juan. You got your hand raised. You got a question?
Oh, yes. So thank you so much for the explanation. I just want to ask about the volume. This volume is a bulk volume or a DRE, sorry, volume, or it doesn't matter?
Good question. So for Titan, it doesn't matter because it's using just a continuum. So you don't have like solid particles and gas, right? It's all mixed together. So generally,
Okay,
what you
okay.
want to use is a bulk volume for that. Uh, for IMAX, you have the option to actually select like what is the volume fraction of particles that you want. So for that, you may try to use a GRE volume as a fraction of your total bulk volume, and from that you can use the volume fraction of particles. But otherwise, I would say that that does not really matter unless you got a lot of gas, right? And so in that case, you want to make sure that you separate the volume of particles stored to the gas volume.
Okay, thank you. And I have another question about the rheology parameter, the MU.
Yeah.
Is a parameter that I should in in the best scenario I can estimate in a laboratory, or how
Yeah.
can I get it?
Yeah. So the Coulomb rheology has been used a lot in like granular flows. So a lot of people have done some dam break experiments or other experiment in a fume to try to calibrate these parameters. Um, I would say that for PDC, it's a little bit different because we're talking about multi-phase flow. We've got some gas, air entrainment, setting of particles, erosion as well at the base. So it's a little bit more complex than
Okay.
just like normal granular flows. So generally, what happened is that there is a relationship between your basal friction angle and your volume, which means that it's inversely proportional. So, which means that if you have a large volume flow, generally you're using basal friction angles that
So,
are lower. And if you have small volume flows, the basal friction should be higher. So
okay.
you can look at the work from Sarah O'Byrne at Montserrat in Sophia Hills. They try to calibrate the basal friction angle based on the volume, the flow volumes. It's not straightforward, but I would say you don't want to use a value that is too small, smaller than 8 degrees, because then the flow is going to become very mobile. And you see already in the footprint how using small values are gonna the flow is gonna spread. It's gonna like overtop ridges that are like several hundreds of meter high. So you gotta be careful. What I would say is that try different values and see, which one seems to be the most realistic for a
Yeah.
particular volume, and start from there. Yeah.
Even if I'm trying, I'm not sure if I can to model dilute by PTCs with this.
Mhm.
Okay, okay. Ah, okay.
Yeah, you can try that. I mean, the best is, of course, to use a model that is made for dilute PDC. So a rheology, like for example, the Bursick and Woods rheology, which is really the one that is using, a gas-rich mixture. So IMX allow you to choose that kind of rheology, not Titan. So for Titan, you can try with like low basal friction angle to see if that match the footprint of your flow. And if you start seeing some unrealistic behavior, of the flow, like overtopping, like very high ridges and things, then try to put some higher values.
Okay, okay.
Yeah.
It's like playing with the value to get
Yeah,
them.
it's a lot of trial and error. I mean, one thing you can do is that if you know the H over L ratio of your flow, you can do the inverse of the tangent of that, and that's going to give you the
Okay.
friction angle. But the problem is that usually you need a lower value than that. So, but that could give you a first order
Okay.
of
Approximation.
the value you want to
Okay.
take. Yeah.
And just the last question, this value, for example, is could be available in the flow that you show of the USGS? This type of
Not sure. I'm
parameters?
not sure if they put the battle friction in the flow that you will have to check. I'm not sure.
Okay.
You will see the H overall. The H overall is in there. So if you
Okay.
want to see what are the typical H overall value for a type of PDC, then it's in there. But I'm not sure they put the battle
Okay.
friction values. Yeah.
Cool. Thank you.
Yeah, you're welcome. Yeah, Leah.
Hi, can you hear me?
Hey. Yeah.
So first one, this might be a little simple, but if you want to reflect a different source like the lateral blast, you would change that vent source to be wherever that collapse occurred.
Yeah.
Okay.
Yeah.
And we can do that in the DEM output
Yeah. Yeah. Yeah.
that,
You
that we
can.
went over in the first week or so.
Yeah,
Okay.
yeah, definitely. I mean, if you guys can try with your own DEM and change the coordinates of the source, and then you can also put a volume. You can change the volume if you want. So the best way to change the volume is to actually look at the formula for an ellipsoid. I think it's in the user guide, and then you can play with the minor and major axis of your ellipsoid as well as the height. And so you can end up with having a pi that is closer to the initial volume that you think is realistic for your case scenario. Yeah. Mhm.
Okay. And the other two questions I had were if I wanted to test like a flow trajectories path, can I input that as like the TIFF instead of like the DEM landscape as itself, or like is there a way to be like more localized in an area, or is it just really running?
Yeah, you can. I mean, you don't have to. So what you want is that just take like a segment of a valley or like some very small scale case study.
Yeah,
Yeah,
like in a
I think you
specific like yeah. Go ahead. Sorry.
yeah, I think you can do that. And then just I mean, it's just going to be the scale that's going to be different, right? So make sure like on the scale parameters, you actually change that scale parameters instead of being like 4,000 meters. It's going to be, I don't know, 10 meters or 100 meters based on the scale of your segment. But yeah, you can definitely do that, and then try just to run it on a small segment. You can also put an initial velocity if you think the flow was
Hmm.
coming from elsewhere, and then you're just passing through that area. Then you can also put an initial velocity there, and yeah, that should work.
Okay, great. And then the last question was instead of like changing the bed angle per run, can we do like a sample of them and get um a more smooth way of running multiple bit angles across, a min to max of that, or what's the most efficient way to see that?
Yeah, I mean, yeah, I think you want to probably like do with trial and error
Yeah.
for all these things that are not calibrated because um, I mean the critical thing is that to make sure that that your velocity in the end is very low. I would say between 0 and 5 meters per second. That will show you that the flow stops because otherwise, if you put a simulation time that is too short, then the simulation is the flow is gonna still be running, and so you don't really have the final run out, right? What you see is just like
Mhm.
the last time step when you stop that simulation. So you want to try with that, and same with the other parameters that are not for the moment. There's no like default value or calibration tests that have been done. Just try different values and see what you get. Yeah.
Okay. Thank you so much.
Yeah. Yeah. All right. Don't see any other questions. So thank you very much. Yeah, we're running out of time. Sorry. So thank you very much. So yeah, try to take your own DEM and then either run Titan 2D or IMAX or both of them. Try. I think IMAX is a bit more restrictive for the format of the DEM. I think it's allow only integer values for the elevation. So just check that. Just look at the actual DM for Colima that we're using and try to get the same format of this. And so let's do that. Put all your results into the Padlet, and then I'll try to look at them during the week, and we can sum up that quickly next week. And otherwise, have a good weekend, and I'll see you next week. Bye.